Good morning, guys, and welcome to week 5 of Astronomy 120. We are actually, this is an important week, and I really want you guys to focus on what's going on this week. This week on Wednesday, of course, we have our exam. The exam is going to open up at 8 o'clock in the morning and will be available until 11 p.m. So I strongly urge you guys to make sure that you're ready for it first, and then at least you plan that day accordingly. Excuse me. If you have other things going on during the day, and I know some of you are actually in high school and you're taking classes in high school, others are actually taking other classes on college too, and some of you are actually working, and under any circumstance you should be able to find a way of doing your exam, either on during daytime, if you happen to be busy on working or other things, engaged doing stuff in the evening, or you can do it actually on at night if you happen to be busy with classes or other things going on daytime. So the exam is open, and that's the only day when it's available, so you really need to plan for it accordingly. The other thing also that is available for you guys, and that is actually an important task that you need to make sure that you're doing, and that has to do with the review for the actual exam. So you have the midterm review, which is available on Canvas and has been available since last week. And some of you actually have taken advantage of it and started it. Others did not as of last time when I checked. You have received reminders from me, and you may and probably will receive reminders again from me before it closes. The review is going to end tomorrow midnight, so you really need to get going with it if you did not start it already. So it's important, you have to do it for 2 reasons. First of all, it's a graded assignment in a sense that if you don't do it, you get no credit for it. You get 0 mark for it, and you don't want that, okay? You would want to do it, and once you do it, once you actually start the review and submit the review, I know some of you actually told me that you looked at it and you start doing the review, but you did not submit it. But you have to submit it. You're going to get credit, full credit, as a matter of fact, for whatever the entire points that are worth. I do that to make sure that you guys are doing what it takes to pass the class. And this is one of them. So you're participating, engaging in the class, and you're doing what you're supposed to be doing to pass the class. So this is one of the things that you're supposed to be doing. So make sure you take care of it. Otherwise, as I was saying, you don't get any marks for it. So it's important on its own because of the fact that it has value. So it's going to go to your grade. Granted that this is going to go to your participation grade, but it's still a grade nonetheless. I said an assignment that is graded. So it's important, okay? Now, the other point that is important about this review is the fact that it helps you prepare for the actual midterm, okay? So if you do the review and you do it thoroughly and you understand everything, and there is nothing that is kind of ambiguous for you, then in this case, you go with confidence to the actual exam on Wednesday, knowing all of these things, and you should be ready for the exam to maximize the maximum possible. Hopefully, you get 100%. Why not? I mean, there is no harm in that. And I mean, in the past, a lot of people score 100% in my exams of this type. So there is no harm in that. And this is not a far-fetched actually thing. So it's available for everybody. And I'm really hoping that as many as possible of you guys do that. So that's really why I'm encouraging you to do the review. I'm giving you incentives, and also hoping that you guys score the maximum for it. It really helps you understand the materials, prepare for the stuff that is coming forward, and so on and so forth. So this is about the review. This is about the actual exam. Because the exam is actually on Wednesday, we will not have a live session because some of you probably will be tied up later on in the classes or tied up at work. During nighttime, you probably have other things going on, and you would want to dedicate the time to doing the exam actually for the time allotted when we decided to meet. That's fine. You can do that. We will not have a live session this coming Wednesday. And that is what we would have done anyway. If we are meeting on campus, we will not have lecture on that day. We will just do the exam. So this is the plan with it. So I'm hoping that you guys take full advantage of it and do it. The lab is not required for this class for Astronomy 120, but some of you are actually enrolled in another lab that I know of, and that is Astronomy 125, because they happen to be in that class that I am teaching, that I'm doing on campus. So Astronomy 25 has nothing to do with Astronomy 120. So Astronomy labs flow with their normal flow. In other words, tomorrow for Astronomy 125 Section 1 will meet, and we will hold our normal lab on Tuesday. Astronomy 125 Section 2, which meets on Thursday, will continue also unimpeded. So the labs for astronomy that are held at least on Tuesday and Thursday have no bearing whatsoever on what's happening in Astronomy 120, whether this section or the other section that I'm also teaching, or another section that I know another instructor is teaching. So those are unrelated. So please do not send me a message, for those of you, of course, who are sitting in Astronomy 125, asking about the status of the lab. The lab has nothing to do with this class and is going to continue the way it is, okay? Now, that is basically something that pops up, especially for the classes I'm teaching where they have actually a lab and lecture at the same time. I'm doing that with them, and they might be thinking that maybe we can do labs because we have exams. Okay, so they are not related matters. So hopefully you guys is clear for you guys. For those of you who are not taking labs this semester, namely Astronomy 125, ignore what I just said. It's not related to you. It's related only to those who are taking labs in the same time lecture for astronomy. Okay. So this is in terms of what's going on. Let me share with you guys the screen so that to see what's happening in this week and where to find stuff. Share. Oops, that's not what I wanted to share. I wanted to share this screen. Okay, so this is, we are on week 5. So this is where we are. We're supposed to be doing units 37 and 38. We're going to talk a little bit about them too. And this is, first of all, where the review is. It's actually from the week before. Okay, so the week before has the review on it. So if you happen to just basically notice the fact that, hey, we have a units in here, models in here, because probably you were not here last week or something, or delayed things, and you're looking for the review is actually from week 4. That is where the review is, okay? And also, since I have week 4 open, we have a homework assignment that is due on the 8th, which is this Saturday, okay? Now, I was hoping that you guys would have done it, and some of you already have submitted it, okay? For those who did not submit it, I would rather delay that and not start it, or not focus on it as much as I would focus on the review. It is by far more important at this point than the actual homework assignment. The homework assignment, you can start on it immediately on Thursday, because it's due on Friday. I mean, it's due on Saturday around 11 p.m. So that is clarifies that point in here. This week, of course, we have the content and we have the normal stuff, objectives and things like that. And we have our exam on the first midterm on October the 5th, which is this Wednesday, okay? That is by far the main thing at this point to focus on. So we have to focus on this midterm by making sure that we do the review for it, which is from the week before, okay? And something else also popped up from this week that we didn't see from before at all. Namely, this is the lunar observation. We really need to talk about that, and I'm going to talk about it today also because it's of its importance. It's a different kind of assignment that you're guys expected to do. Again, you're not going to focus on it as much, at least before the midterm. So the midterm is more important. You could go and see what it says in here, and it's due on November 18th. Don't be basically fooled with this due date. This is a long-term project that has, for some reason my camera was not showing, so I'll make sure that the camera is on. So at any point in here, This is a long-term project that has components that need to be completed on a regular basis. The first component must be done this Sunday. You have to go out and find the moon and see the shape of the moon, the position of the moon, and document that for your final project. You're going to do that week in, week out, okay, for 4 weeks, for a whole month, basically. So this is really, your observations will end toward the beginning of November. Then you will have about 2 weeks to complete your report. So this is what the plan is for this project. Okay, again, the main thing today, the main thing this week is this assignment by far, to complete the review, to get credit for it on its own because it's a graded assignment on its own, and then also to prepare you for far more important assignment in terms of your overall grade, which is the midterm, which is again part of the stuff that is coming down the road. You have other stuff also that was from the week before, namely homework assignment 3. That, if you didn't do it yet, please defer it until after Thursday, okay? After Thursday, then you should, after Wednesday, you should say Thursday, then you can start working on it. That becomes the second one. The third one, and this is the project now that you're going to be focused on to make sure that it's completed. Again, you have other assignments in here. You have discussions from week 5 that is due in about a long time from today, basically October 14th. And you have actually a discussion also from the week before that is actually due this Friday. So you have stuff that is due, and that is because normally I assign things, give you plenty of time to do them, but hopefully you're taking care of them, not on the deadlines. I know a lot of you, or at least some of you, do that, and that is not actually good practice. Better practice is to submit your assignment as early as possible and start it as early as possible. Okay, so those discussions, the one that is due this Friday, you should really have completed it by now. In terms of weight of things, this week, the most important thing at this point is to do the review. That is important, okay? For the exam, do the exam on Wednesday. That is important. You're done with it, then you go to the other 2 things that are due. One of them is on Friday, and discussion from the week before, from week 4, not this discussion. This discussion, you still have ample time for it to do it on October 14th. Which is not this Friday, the Friday after, okay? Then you have after that, you make sure you have the homework and discussion from the previous week to make sure that they're all submitted because they are graded. And then the other thing also is this project that popped up, and this project is, yes, due November 18th, so technically you still have more than a month to basically complete it, but it don't be completely fooled by that due date. And I will go through it to make sure that you know there is actually a component of it that is due this weekend. And then the next week, you will have another component, and the week after, you will have another component extending all the way to the beginning of November, just before the holiday break, just before Thanksgiving break, you will be submitting that report. Okay, so it needs all of these things to be completed in time to make sure you get all of the credit for it. Okay, so that's basically stuff. Meanwhile, of course, you will have other things coming down the road. You will have quizzes and also other assignment, homework assignments and discussions, and basically other things, including another midterm that is going to pop up just before the actual when the project is going to end. So there are stuff that is going to be happening down the road. So please take care of things as they are and do in their due times. Another point that I want to emphasize on is the fact that you should have received a message from me yesterday stating that you would have all of the assignments that were supposed to be graded were graded, okay? With the exception of one assignment that I postponed it because some of you did not submit it yet. And I didn't want to put an added pressure, so I extended it a little bit. So if you did not do that too, please do it too. And that was a homework assignment from the week before, from the week 2. So there are stuff that is needed to be submitted. So hopefully you guys will take care of them and do them. So all of the grades are there. The grade that you see on your Canvas, which is the overall grade, your own overall grade, will be impacted a lot by your midterm. What I mean by that is, if you have, let's say, for example, your grade this is an example of it, may not be your grade. Let's say, for example, you're saying a 75, and you come to the midterm and you score a 95. So your grade will jump and jump a lot, okay, up. And it's the other way around too. Let's say, for example, your grade right now is sitting at 94, and you come to the midterm, you score a 70. So your grade will drop and drop a lot because midterms have more weight than anything else. So that's why I'm emphasizing on it, to make sure you guys maximize from it. There are times where the grade doesn't change at all. I mean, hardly at all. If you're sitting at 74 and your midterm grade is 74, so it's probably going to be the same. Same thing if you're at 94 and you score a 95 or a 93 or even a 94, then your grade is probably not going to change. So in other words, the midterm will make your grade change a lot. Although you get all of the grades in here and you seem to be in a place, whether a place that you don't like or a place that you like, please be mindful of the fact that the grade overall will be impacted a lot by what happened on Wednesday. That's why Wednesday is a very, very important day for you guys. Make sure that you're ready for it 100% and doing that as the utmost important thing. Okay, enough talk about these things. Okay, so let me share with you again this thing in here, the lunar object, because the lunar observation project, I'm sorry. So that's an important thing because it's something that we didn't do before. So we need to understand what's going on with it. Again, you're supposed to read all of these things. Once you read all of that, you're supposed to do stuff in here. So forget about it. So if I don't have time, I want to do what basically I need to do just to pass, okay, to get a good grade for this one. This is a good starting point, is to look at the rubric and how you're going to be graded, okay? The rubric in here says that I need to do question number 1. So I really need to see what question number 1 is. Here is question number 1. Which position A through E of the moon best corresponds with the moon phase shown in the upper right corner? I don't have a picture in here, so probably it's in the instructions in here. So I'm going to download this PDF or Word file. It depends on whichever one you like, okay? So either one of them should work fine. If you're more comfortable with Word, you can do it with Word. If you can do a PDF, that's actually better. So I'm going to click on it and open it. Once it opens, do you see it? Is it visible? Do I need to stop sharing and share again? Yes, no, maybe. Since I don't have any reactions, I'm going to just basically stop sharing it. I know most of you are not here to really tell me that. So I'm going to share again. So again, this is what you're supposed to do on the PDF file. Note that I am using a browser to open a PDF file. This may not work with your browser, especially if it's an old browser. It may not give you this shaded area in here. What that means is I can put my name in here, okay? Could put my name in here and start typing stuff in here. And as I do, I can include more things. The reason why I'm showing that is that I really need to put my name and anybody else who worked with me, okay? John, okay? Well, Doe, for example, worked with me, okay? So anybody who worked with me, technically, I can write their names in here in the report too. You are supposed to do that, okay? Then once I'm done with that, then I'm going to go down, and here is what it's referring to. I have the sun in here. I have the moon in different positions, A, B, C, D, and E. And the question is asking me here, question 1, which position A through E of the moon best corresponds with the phase, the moon phase shown in the upper picture, okay? Is it in position A? Is this in position B? Is it in position C? Is it position D, or is it in position E? If you read the phases of the moon, you know the new moon is going to be somewhere in here. And then at some point it's going to be crescent, at some point it's going to be quarter moon, whether here or here, and at some point it's going to be full moon, or so on and so forth, okay? But which crescent am I talking? At some point it's going to be gibbous. Is this gibbous waning or waxing? Is it going to be crescent waxing or waning? Depending on all of that. This is from Unit 8, by the way, a long time ago that we started it. So again, you could go to Unit 8 and refer to it, and you're going to write an answer in here. The position that corresponds to this one is position, I don't know, A or B or C or D or E, whichever way you choose. And you're going to put your answer in here and try to justify your answer, okay? Why do you think so, okay? And then if I choose a corresponding, let's say, for example, for the sake of argument, I chose A. Okay, that's it. I nailed it. It's A. Okay, for example, okay, please don't write A if you think it's not, okay? Or if you think it's truly A, then it's your call, okay? So let's say, for example, for the sake of arguments, it's A. Then I know it's not B, and it's not C, and it's not D, and it's not E. So what I'm saying in here, I think, I may be wrong, of course, that A is the correct answer, and then, or B, then B is not, C is not, D is not, and E is not. That's basically what I'm saying. So if I go to question 2, in the 4 boxes below, sketch how the moon would appear from Earth for the 4 positions that you did not choose. Be sure to label the sketch with the corresponding letter indicating the moon position. So I believe the answer probably was A here. Then in this case, B, how does B would look like? So I come in here and write B and draw a sketch in here. So what I can do in here is, if I don't have a drawing tool on this computer, so I can click on this one and basically upload to it. Now it's not working. The reason why it's not working is because the fact that I'm using not a browser, that the browser doesn't support uploading. So what I'm going to do is, instead, I'm going to stop sharing, and I'm going to download that same file on my desktop. So let me go back in there, download it on my desktop, and open it with a browser, okay? Well, I'm sorry, with Acrobat, okay? File, open. I'm going to find it in here on my desktop. So the minute I find it, I will open it, okay? Okay, where is the project in here? This is dated October 1st. That's not the one. I need the form. This is what is known as a fillable form, okay? Okay, so I have the form now. Okay, so let me go back to share. Let me close the share now button, share again. And now I have it open with Acrobat, okay? So technically I was saying in here, you put your name, you answer the first question. For some reason, it's not displaying. Here is the first question. So I answer the first question, and I answer the second question, and now I'm going to upload this one. So you see here the difference between the first and the second? Using it in Acrobat, it gives me the option to choose an image, and let me prepare an image in here. Upload, and let me go back to preferred place in here to images. I'm trying to find an image on my computer that is actually okay. So let me go back, images. Astronomy, images, and let me just take this image folder, okay? So let me go into select this whole folder path. So I'm gonna browse, and when I browse, I'm gonna put the folder path. So okay, so I found the images. So I'm gonna pick up an image in here. Okay, it's not necessarily that I'm going to. So I uploaded an image, and the image is in here. So in other words, what I could do in here is, this is a self-contained thing. So I could draw it by hand or draw it on the phone, upload it to my computer, and then upload it in here to my report. So they're saying, since I said the other one is A, this is B. So what I'm saying in here, I already hand drawn how B would look like. Okay. Since this is what I believe the answer to the first question is, then how does the moon would look like when it's in position B? I would draw it by hand and then upload it in here. Same thing. On position C, how the moon would look like, and the same thing, how position D would look like, and then on position E, how the moon would look like. So this is basically, now I'm done with that part. I come in here and do my lunar observation. My first lunar observation is on or around October 9th, 2022, which is Sunday. So this is my first lunar observation. When I go to the moon and look at it on that day, so I am going to put in here, let's say, for example, I did actually my observation on October 9th. So I'm going to put October 9th as my day in here. But then I have to put the time when I looked at the moon. So the moon, probably I looked at it at 9 p.m. or 10 p.m. or 8:34 p.m. or something like that. Or maybe it was not visible until like 7:30 in the morning before doing anything else. So it was visible the day after on Monday morning. So this date, if it's on Monday morning, so this date is not correct. Then it's going to be October 10th, and then the time is 7:30 in the morning. So it's going to be 7:34 a.m., for example, okay? And come in here, the shape, how the moon looked like. Was it a gibbous? Was it a quarter moon? Was it a full moon? Was it a new moon? Or whatever I make that call. Obviously, if it's a new moon, I will not be able to see it, but I will basically infer based on my observations that the reason why I didn't see it is because of that. Now, you have to name the face. So here, you're going to just describe the shape. Is it a full circle, half circle, quarter circle, bulging one way or the other, or something? Here is when you name the moon, and you're going to tell me its position. So what I mean by position, it's not an exact position. It's not going to give me degrees or right ascension or declination or anything like that. You're going to look. Right now, this is north, this is south as far as I am sitting right now. This is east, this is west. So wherever you find the moon, let's say, for example, it's in the southwest, okay? Where you saw it, okay? Or southeast, for example, okay? But then, which side? Was it closer to the south, or closer to the east? Number one. Number two, was it with the horizon, or was it in your zenith, or was it somewhere in between, exactly, or closer to the zenith, or closer to the horizon? What I'm looking for when I say position is not an exact position, but relative to your position where you are. You have to tell me where you are, okay? Because some of you are not in here in Southern California, probably you're in Northern California or some other latitude. So your viewing point may change a little depending on where you are, okay? Obviously, it's not going to change unless you go to a different location, completely different, then it's going to give you a different viewing at different times. That is what you're supposed to be doing. Again, let me go back into that thing, share. Okay. Again, you're supposed to, not there, not that. Let's actually, you could do it all also here, but in here, you're not, click on this, it's not going to help you. You have to use it on a outside of the browser. At least that's my experience in here. So your experience may be different, okay? So I opened it on the browser. After you do that, you do something similar in the sense that you upload the shape of them. You can do it hand-drawn, the shape of the moon, okay? You don't have to take pictures. And if you take pictures, actually, the picture will not be as accurate as when you see it, okay? So you're going to also take a hand draw it and then submit it. And you're going to do the observation on the October 17th, and then you have October 25th, and then another observation November 8th. By then, you're done with your report, and you're going to conclude your project in here. Okay. What is the deal with those dates? Those dates are important. You will be receiving reminders the day before around noon to tell you that you go out on this day, on that day. Let's say, for example, we're doing the first observation, which is technically on Sunday. On Saturday, you need to go out and basically spot where the moon is. So actually, your observation extends the day before. So you go out and, okay, you look at it, you find it, you're in good shape, you document the time and the shape of the moon is on that day. And then your day observation, when you actually do the observation, and report it. Now, let's say, for example, the day of the observation happened to be not good because of the clouds on that day. Well, then you wait for the day after your day of observation, and you actually confirm your spotting the day before. If that too is not inconvenient because of the weather, then in this case, at least you didn't miss day one, which is actually where your observation is going to be. So that becomes your official observation. If your day before does not yield anything because of the fact that you couldn't find it, or because of the fact that it's a cloudy day, then you still have the day of observation and day of the third day. Technically, in Southern California, we really never have 3 days of inclement weather. So we should be able to get it one day or the other out of these 3 days. The day before observation, and the day after observation, and the day of the observation. So technically one of these 3 days should work. Now, you go out and you look for it and you don't find it. You go out early in the morning, in the evening, I'm sorry, later in the evening, and you don't find it. Then you wake up early in the morning, most likely you're going to find it, okay? Sometimes 10 o'clock in the morning, it's still visible. Now, if you don't find at any of those times left and right, that's what you're going to report. Then you speculate, was it really a new moon? If it is, then you should expect what to see later on a week from there, which is the next phase, quarter moon. If it is not, then there was something wrong in your previous observation, so you need to document these things. This is a long-term project. It's important, but it is not as important, as I was saying in the beginning, as exam 1, midterm 1, which is this Wednesday. So please focus on that. That is by far the most important thing in here. Are we clear on that? Sounds good. Yes, maybe. Can put in the chat, okay? Okay, very good. Thank you. Okay, so we're going to move on to the content of this week. So let me go back into that thing in here and make sure I have the back to the modules of this week. Week 5. Go back to the objectives. And let me share that link. So in terms of content this week, we'll be focused on basically units 37 and 38, which are not part of this exam. They're part of exam 2, midterm 2. So at this point, the content in here is not going to be as relevant to the this midterm as it is going to be for the next midterm. And this is actually a departure from what we were up to unit 35, okay? Unit 37 introduces a new idea that we're moving towards, and namely the fact that we're focused more on the planets now in the solar system. So we want to understand them and see how they look like, and the objects in the solar system and everything else. Before moving to those things, what we want to do is actually learn about the Earth, because the Earth is actually a handy object that is within our reach, where we can actually study and learn about it. And that's really the plan with units 37 and 38, is to give you that insight. What we learn from Earth, take that and hopefully explore it and extend it to other objects in the solar system. So unit 37 talks about the Earth, its composition, and how do we know these things? Obviously, we learn through it using earthquakes, okay? And then we're going to learn about it inside. A lot of these things are actually hard to also study too. So we're going to learn about its structure, its magnetic field, and so on and so forth. Once we move on to other planets, so we're going to do a few planets, we're not going to do all of them because we don't really have enough time in the semester to do all of the planets and go all the way to the solar system and finish it, and then go all the way to the stars and then galaxies and things like that. So we're going to only select a few planets and then a few moons, and then we have some object from the solar system, and we basically make generalization and make comparisons between the object that we don't study. And hopefully you guys have enough units in the books that you go through them and understand what the others, especially if you have a question about those. And as I was saying in here, then we're going to study its atmosphere, because the Earth happened to have an atmosphere, and it's not unique with that feature. As a matter of fact, it's not the densest atmosphere in the solar system. Relatively speaking, is actually the Earth does not have much atmosphere at all. It's a very, very thin layer compared to its overall structure. Venus, for example, has tremendous atmosphere. It has far more atmosphere than the Earth does. So it's much thicker atmosphere. The composition of the Earth's atmosphere is different than that of Venus, though, because Earth's atmosphere is mainly nitrogen, and with some traces of oxygen, not some traces, with some oxygen in it, because 20% is not traces. So it's mainly nitrogen with some oxygen in it, and then some traces of other elements, namely carbon dioxide and water and other lighter elements in the atmosphere. Venus, on the other hand, for example, has mainly atmosphere. Its main atmosphere is mainly carbon dioxide, actually, with some traces of other elements, actually, and those elements that are there. So let me pull the units in here. So the other elements that are in the atmosphere are actually water, maybe, but the main thing actually is sulfuric acid. That's really what the problem of that planet is. So Venus is completely different, but it's mainly let me put the notes in here. I'm trying to get my notes up and running in here. So for Venus, it's mainly carbon dioxide, as I was saying, with sulfuric acid on Venus rings. And we're going to talk more specifically about Venus and why we have to really focus on it. On the opposite side, for example, Mars has a lot thinner atmosphere than the Earth does, but its composition is actually has a lot of carbon dioxide. It's mainly actually carbon dioxide, so it's not too different than Venus in terms of composition. But in terms of pressure, it's a lot different. Venus is has far more pressure than the Earth does. It's about 92 times more atmospheric pressure than the Earth does. And Venus, on the other hand, is about 1% or 2% out of the atmospheric pressure of the Earth. So the Earth sits in between them. But that's not the only two objects with atmospheres. I mean, we have other objects in the solar system with a lot of atmosphere. I mean, like the outer planets, they have tremendous atmosphere. They're called gas giants for a reason, and because they have a lot of atmosphere. And then to draw another comparison with another object in the solar system, namely the moon is Saturn, namely Titan, its composition is not too far from that of the Earth. It's mainly nitrogen, true. So Earth and Titan share that property. And not only that, the atmospheric pressure on Titan is not too far from that of the Earth. As a matter of fact, slightly higher than that of the Earth. So if you were to stand on Titan, temperature is so cold, of course, you need to have protective layers against the temperature, because temperature will basically freeze you to death. So if you have enough basically things to wear, you should not feel more pressure. I mean, you will feel a little bit more pressure, but not that something that is unbearable. Like, for example, when you stand on Venus, which is going to crush you, or you're not going to feel basically that your insides are coming out, you're going to explode, like what happened to you on Mars, because Mars has a lot less pressure. So that's basically something that is feature that is similar. Of course, Titan doesn't have as much oxygen on its surface as the Earth does, but it has a lot of water, also frozen water, ice basically on its surface that you probably could basically defrost and make it into water that you can drink, and also decompose it, make oxygen out of it that you can breathe. So Titan actually is a very promising moon that is in the solar system that can be probably easier terraformed than anything else. Provided you can heat up the place where you are to a comfortable temperature, you should be able to survive in that moon. Okay, so you guys saw the movie Interstellar. That's what they end up being at the end of the movie. They end up in that moon where things are in that place. So that's basically where, I think that's where the end of the movie ends. So on the moon Titan. Anyway, the point being in here is that this is the object that we're going to be focused on, namely the Earth. So we have to start somewhere, and it's much easier to start in a place that is more familiar than anything else. So let me share Unit 37. So again, Earth as a terrestrial planet. So this is the subject. These are the same stuff as I was talking about in terms of the objectives for this one. So the Earth has is really a rocky planet, and it's mainly what the rock is made up of two elements: silicon and oxygen. They happen to be on the periodic table. Silicon is a transition metal that is used in semiconductors a lot. And actually, if you go to the beach, that's what the sand on the beach is mainly made up of. So it's silicon, and actually any dirt on Earth has a lot of silicon in it, and silicates, it come in this combination of oxygen and silicon that make up this oxides of silicon. So that's basically what the silicate is. So that's the main composition, at least on its crystal. That's what you see, but its density is a little bit high. And actually, it's not high. It's the highest density in the solar system as far as large bodies are concerned. Okay. It's 5.5 kilogram per liter. It's denser, of course, even then, of course, the sun is less dense. Obviously, if you count the core of the sun, it's denser, but because of tremendous pressure, that's all from the upper layers. Otherwise, in terms of composition, the sun is mainly hydrogen and helium, whereas the Earth has all kinds of heavy metals on it, especially inside the core, where there are two dominant metals, namely iron and nickel. And then you have the other lighter elements in the upper surface. So if you combine all of these elements, it gives you a density of 5.5 kilogram per liter. The next object that is densest in the solar system after the Earth is, of course, Mercury, which suggests that the composition of Mercury is not too far, especially in terms of the core. It has a big core also in it to account for that high density. And then, of course, comes Venus, and then you have the moon and Mars later on. So those are denser objects, okay? And the density of the surface, of course, is not that high. So you need really heavy materials to account for the density in the inside. So this is the composition of the Earth in terms of different materials. Obviously, there is iron in the Earth with a lot of quantity on it. Overall, the Earth is mainly a third of it is iron. But on the surface is only, or on the crust, actually, it's only 6%. So where is the rest of the iron, then you ask? Well, it's inside the core, inside the Earth itself. So you have a third of the Earth is iron, but only 6% in the crust. So the bulk material of the iron is inside. As opposed to the oxygen, again, a third, the other third. So 66% is basically between these two elements, iron and oxygen. Okay, so that's the composition overall of the Earth, not 66, 62, which is still 2/3 basically. So, but the oxygen is mainly in the crust, as opposed to, as I was saying, the iron. Silicon is similar to the oxygen, although in the case of the silicon, it's less quantity than that of the oxygen, but it's still mainly in the crust than that of inside the Earth. If you look at magnesium and nickel, which are the two actually other main elements. Did I mention nickel in here? Probably it's not. Yeah, nickel is here. So those are actually, the reason why nickel and iron are always listed inside the core is because of their magnetic properties, okay? And Earth has magnetism, we're gonna talk about that. So, and they're the ones who cause magnetism. So in addition to that, you have magnesium. So look at it, 14 plus 16, that is 30. Plus 30, that's 60. Plus 32, that's 92. So 92% of the elements are just between the first four: magnesium, silicon, oxygen, and iron. That's basically what the Earth is. It's mainly iron, and that accounts for that density of 5.5 kilogram per liter. So you really need this heavy, dense materials to really account for that density. Of course, nickel is not far behind. I mean, it's kind of far, but at least it's in terms of the core, it's actually the second one. And then you have sulfur. Those are 2% and 2%, and then another 2% of calcium. And calcium is mainly actually in the crust also, similar to the others, in addition to aluminum, because aluminum's density is a lot less than that of the other materials. So it stays to the top. Remember when we were talking about how planets basically cooled after they were too hot? When they cooled, they differentiated. So the more denser materials go inside the core and the lighter materials stay up. And aluminum is one of the lighter materials. Aluminum density, if you have a spoon, for example, made of aluminum, compared to a spoon that is made out of iron, and you will see a big difference. I mean, if you have a pen that is iron, what is that they call it? What is it? Iron cast versus that of aluminum, and you will see they are roughly the same size, but one of them is a lot heavier because iron is far denser than aluminum. Aluminum will stay to the top, will float more or less. Okay. So, and then you have some other elements, and here and now we're talking about traces of elements, and you can see their abundance, relative abundance. How do we know all of these things? How do we know the structure of the Earth? Well, in this case, I have a slinky. I should really have brought it with me. You have two kinds of waves, okay? I know when we did, some of you are sitting actually in my astronomy class, and we talked about waves, especially when we talked about this spectroscopy, okay? And how light is a wave. So there are two kinds of waves, okay, that you see in nature. If you take a string and you stretch it and keep it stretched, and don't disturb it, make sure that it's equilibrium, nothing will happen to it. Same thing, if you go to the surface of the water, in a pond, for example, where there is no wind blowing whatsoever, so the pond is calm, there is nothing in it. Same thing, in this room, for example, where I'm sitting, or where you're sitting, you could turn off all the sound sources. For example, if I stop talking, that is a calm air. It's not being disturbed, okay? So in those situations, we don't have waves. The minute I create a disturbance, whether I start talking, whether there is a noise source in the room, whether I drop a rock on a calm pond, for example, of water, or I take a string, for example, and disturb it from one end to the other, start basically, or playing the guitar, for example, then in that case, I have created a disturbance. So the medium is no longer at rest. It's no longer at its steady state. It's now being subject to oscillations in one point of it. Those oscillations, they don't stay in that point. They propagate, they move around, okay? There are two modes of oscillations, though. There is an oscillation that go, in the case of the string, up and down. The string is stretched. So we call this one transverse waves, okay? They go in the direction perpendicular to the direction where the wave is propagating. And then there is a compressional waves or longitudinal waves. I could take a slinky, for example, and stretch one side of it, compress, I should say, one side of it, and let go. That compression will propagate throughout the entire medium. I could stretch it also. I could have the slinky basically at rest, and then I could stretch two basically rings next to one another, and that stretching will also propagate similar to the compression. It's the same thing. Same thing. On the sound, for example, what's going on in this case, the minute the sound is made, what you're doing, you're exerting a pressure on the immediate vicinity of the sound source, and that pressure, that compression of the air will propagate from point to point to point to point to point to the other end. So there are two kinds of waves, sorry. There is compressional waves or longitudinal waves, and then there are transverse waves, okay? Which in the case of seismic waves, they're called the shearing waves because they tend to take the surface of the earth and move it against one another. Just like when you take a piece of paper, for example, what is this thing in here for, okay? And you rip it apart from one end to the other. So it's a shearing wave. They call it the S wave in the case of the earthquakes, okay? Versus a P wave, which is a compressional wave, which is similar to how the sound propagates from point to point, or a slinky, for example, point to point. By the way, the slinky also can exert a shearing effect to it also by moving it up and down. So those are the two types of waves. In nature, waves happen in a combination of both of them. In the case of the lab, for those sitting in Astronomy 125, in the case of the lab, light actually is a transverse wave, similar to the shearing, basically, wave that happen in the seismic waves. So this is basically something that, and we're coming down to this stuff down the road, by the way. In midterm 2, we will be focused more on these things about the waves and so on and so forth. So let me go back into my notes in here. So again, you have the first one, you create a compression in the top in here, and that compression will move. So the first time it was near the end in here, and the compression is going left and right, and it's moving to the left with the arrow in here being pointed. So it was in there, now it's somewhere toward the end in here, okay? So let me grab my pen in here. So at some point, this is where the compression was. And the compression now has moved to this side. So note the direction of oscillation is left and right, and the wave is moving to the right in this case. So this is a right wave. Because I could have done the same thing. I could have compressed it from this side, and the wave will travel to the left. So I could have potentially have it move in the opposite direction. But in this case, the second case, which is case B, what I do in this case, I disturb it up and down. So this is basically the disturbance in here. It was moving down. So this is the straight of the slinky. So in this case, I moved it down. So the disturbance at some points is moving up and down. So this is basically down. This is up, by the way. And this is actually where the medium is supposed to be at rest. Okay. So this is where the medium is supposed to be at rest, but at some points it's up and down. And this is the shearing, basically, or the shear waves. Okay. So this is transverse. and this is longitudinal or compressional waves. This is compressional. Sound is compressional wave. Light is transverse wave. But of course, we don't care about that. These are in general. We care about the seismic waves, and the seismic waves, they come in two shapes. If you happen to experience an earthquake, you will see that the one of them comes before the other. You have the compressional waves that come first and then followed by the shearing wave, okay? One of them moves faster than the other. So that's why birds and things like that start to leave their nests and leave their especially if they're in the ground, because they know that the earthquake is coming, because they can sense it. They can sense the first one, so they can predict when the second one is. One of the properties of the shearing waves is they don't propagate through liquids, because try to take a water, for example, and try to create a disturbance that go up and down in it. In the case of a medium, it's going to die immediately. Okay, it's not easy to shear it, to basically break it down. Whereas in the case of the slinky, it is. So that's why basically a wave, an earthquake that happens in a point of the Earth we will not receive the S waves on the other side, but we will receive a P wave in here on the other side, depending if we can find by triangulation basically where the source of the wave is. And this is where the observer is. This is another observer. This is another observer. These are universities all around the place and government agencies that collect data on earthquakes all the time. And based on that, this observer will get nothing. It's like a shadow. There is nothing in here, neither S nor P waves. This one will get only the P waves, because the shearing waves are blocked when they went through the liquid part of the core. And this one will get both of them, because there is no liquid, there is nothing, so he'll get both of the data. Of course, they will be separated in time. Based on that, you can deduce where the liquid region is for this event. You do it again in here, this is another earthquake, you can actually cover the other rest in here. If there is another earthquake in here, or in the opposite direction, you're going to cover, and then you will have a shape of the core of the Earth just by studying that. Because of that, now we have actually a Mars lander that basically put a probe about 2 meters down, or I think about 2 meters down at least, on the surface of Mars, listening for Marsquakes, similar to earthquakes, okay? Similar to what happened on the Earth, earthquakes. So we're trying to do similar studies, at least on the planet Mars, to see how its Earth is, how its quakes are. And it detected InSight that would landed in 2017, detected a lot of quakes actually on Mars. They're less intense than the others of the Earth, but they do happen also. And that is giving us a lot of insight into, that's what the name of the lander is. It says put the probe in here. And that's give us a lot of basically information about the structure of the planet. Hopefully we can have more of them to have more study. But at this point, it's enough at least to deduce the shape of what's going on inside Mars. So it's a useful thing. I mean, to take things that we know from Earth and take them to other planets and study them. So this is basically the resultant of all of this. The Earth has 4 layers. There's the crust, there's the mantle, there's the liquid core, and the solid core. So that's basically what comes from this, all of this study. So this is its structure. The solid core is solid because of tremendous pressure. This is because of the heat, it becomes liquid. And then as you move up and up, it's going to be more of a hot, yes, but not as hot as in the side. Because the Earth is spinning, and because here you have metals, and the metals are rubbing against the liquid part of it, and that creates currents, electric currents. Those electric currents are responsible for the magnetic field of the Earth. Again, the heat that the Earth has are 2 sources, really, mainly. One of the heat sources is the relics from the time when it formed, okay? And the other one is from radioactivity. So this is basically how Earth is hot inside. So this is caused by differentiation when the Earth cooled from when it formed, because remember, when the material came together, it lost potential energy and became kinetic energy. Kinetic energy is heat. And then in addition to that, the Earth continued making more heat, which brings me to another question. What's going on with Mars and Venus? Well, Venus should have both of these too, similar to the Earth because similar size. Mars is a lot smaller size, so it lost most of its heat because it did not have much to begin with. So it cooled down, at least relatively speaking, compared to the Earth and Venus. And also, it doesn't have a lot of materials to begin with to sustain its radioactivity. So its radioactivity also decayed more, and basically Mars lost most of its stuff. So the same thing actually with the Moon too. So the Moon and Mars at some point in their past were just as geologically active as the Earth is today, but they are not as much because they don't have a lot of material to sustain that geology. Same thing actually with Mercury too. But Venus, on the other hand, and this is why we have to really get into next week to start to see what's going on with it, why it's so different. Temperature inside the core is very hot. Actually, it's hotter than that of the sun. Okay, the surface of the sun, not the inside of the sun. The sun inside is in millions of Kelvin. Okay, one way for the Earth to get rid of its excess heat is to do convection. So in the mantle, so part of it is moving up, and the other part is moving up because again the hot is going to have less density and it's going to rise. And when it rises, it cools down, so it falls, and you have this convection layer, similar to what happened in the bubbles that form when you're making your soup, basically on the oven. So basically, what you have in here, immediately in contact with the range, you have a lot of heat, and the material that is immediately in there that is going to be hotter, so it's going to rise, and then it cools down and falls, and the bubbles form in the case of the soup. So the same thing. So this phenomenon of getting rid of heat is called convection. This is one of three ways of getting rid of excess heat. So this causes basically the formation of different plates, okay? And you have plates in here that push against one another, and then you have a subduction on the Earth's surface between one plate and the other, that one goes on top of the other one. This creates a lot of dynamics in terms of the surface of the Earth, and this is the cause of the plate tectonics on the Earth. So that's what causes them. This is an interesting question because why Venus, for example, does not have plates? So how could Venus get rid of its excess heat? Well, in that case, the heat builds up until some point where actually volcanoes erupt on its surface and basically produce more gases than that of the Earth. Because we'll talk about that down the road. Venus does not have this feature. Earth does. Okay, Earth has this nice features on its surface, which is the plates, and the plates play a major role in getting rid of the excess heat of the Earth. Okay, disposing of it, and they build more pressure, and that can cause other problems too. In addition to volcanoes that form, also earthquakes where the two basically plates meet, and that's why if you look at the plates on the Earth, those lines where plates meet are actually the active lines for volcanoes and earthquakes and all kinds of things that happen with them. And overall, these plates move in and out most of the time. They're not stable, not most, all of the time they're moving. And at some point, they were actually closer to one another. For example, if you look at South America and Africa, they felt like gloves. In the past, they were in the same basically structure, and then it broke because of the motion of these two plates. And it's actually continuing moving. So the Atlantic Ocean is still continuously increasing in size. Okay. So this is some of the features on its surface. This is how it was in the past. At some point, the entire planet was only basically one big continent, and then the plate starts to drift and move and around and things like that. This has a major impact on the surface of the Earth because when the plates were very close for another, when the planets cool, they cool a lot, and it takes they don't really dissipate, they don't really heat up as much. So this really has tremendous implications on the weather on the planet. Whereas right now they are more regulated because they were actually below for the most part below the equator. So that's why they cool and they retain a lot of their cooling. So this really had a major impact. Actually, this triggered a long ice age. For the most part, the Earth was icy, basically planet for at least the Earth part of it, the continent part of it. I mean, that's really how the Earth looked like for a long time, and now it's here. So this is 650 million years up to today, and how the plates are moving, and they're not stationary, they're moving still. Again, I mentioned the core of the Earth that is metallic and it has motion, and this creates electricity similar to how you have electromagnets basically form a magnetic field. The Earth has a north pole and a south pole. Again, similar to a magnet, and you have these are the field lines, and they emanate from the North Pole to the South Pole. And this plays a major role because of the fact that energetic particles that come from the sun in here moving at tremendous speeds, namely protons, really for the most part. Protons are hydrogen without their electron, okay? Because that's what the sun is made up mainly of. So when they come in here, they spiral and they fall in the North Pole. If an electron comes in here, and that's the other component of the hydrogen, it's going to spiral and actually going to fall in a different direction, okay? So when they hit the Earth, the atmosphere in here on the Earth, not the Earth itself, not the ground, they have tremendous speed that they create, they basically ionize the material in this side, and this ionization results in the materials basically losing that excitation. So they get excited when they hit with fast-moving particles. Then when they dispose of it, they emit light, and light can be in different colors, and that is the cause of the auroras. So that light that is emitted by the materials in the upper atmosphere trying to go back into their DX, they get de-excited going back to their ground state. The magnetic field of the Earth was neither in the same direction, and it changes. And actually, if you look at the Earth mantle itself, you will see the Earth crust itself, you will see a history of magnetic reversals. So when I was describing in here, the North and South Pole, at some point they reverse and they move. Actually, there is a big motion right now for the magnetic field of the Earth. It's not really aligned, first of all, with the North Pole, which points to the North Star Polaris, and it's moving around. Okay, so it's not in the same place, and it's moving all the time. So that will not cause, by the way, a reversal of the motion of the Earth. In other words, the sun will continue to rise from the east and set in the west, even though the magnetic field changes direction, because that's the magnetic field. It's not the rotation of the Earth that's going to be changed. So that's just to clarify that point so that you guys are not confused about it. Because we don't have a session this coming Wednesday, so I really need to make sure that we also cover some of the stuff from Unit 38, okay? So Unit 38, deals actually, because up to this point we were talking about the Earth, namely crust and structure and so on and so forth, but Unit 38 deals with the atmosphere, which is really a continuation of the same thing. So the Earth has an atmosphere, and relatively speaking, it's less than the other elements that we talked about in terms of Unit 37. The Earth, first of all, before the atmosphere, has a hydrosphere, and the hydrosphere is basically the water on its surface, because the Earth is mainly really water. It's about 70% water, and then the other part is about 30% is the land. The atmosphere is really due to the fact that you have gas weighing on top of the other gas. So this, the analogy for it, if you stand right now, wherever you are, sitting or sleeping, or doesn't matter, there is an amount, if you look at 1 meter, basically, if you step, put one foot in here and put the other foot in here, but you step, long step in here, that is about 1 meter. So if you step 1 meter and another 1 meter on this much, there is 100,000 newtons, or about 10,000 kilograms of air sitting on this. So this is a column of air that rises all the way to the upper atmosphere. This is how much it weighs, about 10,000 kilograms, about 20,000 pounds, basically. That's how much the air will weigh on a square meter. This is what we mean that by the pressure, the atmospheric pressure, 1 ATM, 1 atmospheric pressure, that's what the word ATM stands for, not the bank thing. Atmospheric pressure, it's about 100,000 Pascal. To be more specific, it's 101,300 Pascal. And the Pascal is a unit, so the PA is Pascal, is a unit of pressure, which means a Newton per square meter. It's in honor of Mr. Pascal, who made work on this area. And Newton is a unit of force, okay? So that's basically what we have in here. So this is the pressure, the atmospheric pressure. You look at the atmosphere, it's made up of mainly of 2 regions. You have the troposphere, which stands about 10 kilometers, basically, in height. This is where most of the planes fly, okay? So it's about what, 30,000, 40,000 square feet? 30,000 feet, 40,000 feet, that's what I meant to say. So that's basically the height of the planes, okay, to the extent with which they go. When you are at this height, the pressure drops. Remember, it's 100% pressure on the ground, and then it starts, the density starts to drop to about 50% at that point, okay? It drops a lot. When you are at 20 kilometers, you enter the new region of the atmosphere, which is the stratosphere, okay? the stratosphere has the ozone layer, in this case, which stands in it, and then has the ionosphere, which is a region of space that is ionized, meaning that at this point, the particles are moving so fast that the atmosphere lost, that some of those particles lost of their electrons, so they are charged particles. The ionosphere plays a major role in telecommunications. So imagine you have charged particles in here. That's what the ionosphere is. They lost electrons, okay? So, and you have a radio signal that is moving at very long wavelength. When it hits this one, as if you hit a mirror, so it bounces back. And this is the essence of the telecommunications. So you have an antenna that is broadcasting the signal, and that antenna sends the signal, and now you have your receiver, your TV home, okay? Or your radio that takes that signal and comes back with it. So this is how telecommunications uses ionosphere initially. Actually, it's still today to use it for telecommunication, for long wavelength, for radio telecommunications. So it takes advantage of that, okay? Bounces off of that layer. Okay, again, the ionosphere, I mentioned it, so it extends all the way to 80 kilometers. It is located above 80 kilometers, the ionosphere, I'm sorry. So this is the one that I was talking about in here for AM signal, for amplitude modulation signal. Because on your radio, if you know, I know some of you now, you don't know this thing because you don't have radios anymore. So we do probably some. We have AM radio and we have FM radio. FM is frequency modulation radios, and they use different technology, and they don't really go that far. And AM radios, they use amplitude modulation, and those, they go very far because they take advantage of the atmosphere that sits about 80 kilometers. So you have a signal that goes all the way 80 kilometers, so it's gonna go far and gives you more coverage that way. So this is one of the things that takes advantage of it. So the ionosphere is an important layer actually of the surface, and that is actually where the auroras happen also, the ones I mentioned from the previous unit. And this is because the Earth has a magnetic field. So the particles, as they are moving in here, they put pressure on the atmosphere of the Earth. So in here, the shape of the magnetic field, the field lines, they stretch on one side, and they basically compress on the other one. And they create this Van Allen radiation belts that are basically of charged particles super fast, and they are basically going around left and right. One of the questions that people challenge on the astronaut that went to the moon is that how could they go to the moon where they have to go through this two belts that are of extreme basically radiation that could kill anything? And that's true. Well, in that case, the navigation happened to be in a direction in such a way to minimize that transition. So that's really something that you could do. But the thing with it in here is that forms those aurora borealis or the aurora australis, the two kinds of the northern lights or the southern lights, and they form depending on the charged particles, okay, and depending on the direction of the magnetic field. So that's the light, because you have again an atom that was, first of all, it's ionized to begin with. It has only one electron in here. So the electron moves to a higher energy level. Okay, let's say, for example, for the sake of argument, the electron ends up in here because these particles, they come super fast. So they're going to knock it out of its orbit around the nucleus. So somewhere here is the nucleus of the atom. So they're gonna move it up. So in this case, it's going to transition back. It wants to come back in here. So depending, if it comes straight in here, it's going to be a very, very high frequency wavelength. So it's going to be probably blue light. But it could cascade down. It could just go here first, and then from here to here, and then from here to here. And those are short wavelength, so that's red. But for a specific atom, yes, it could be one or the other, but there are a bunch of them. So you have the entire spectrum and the beautiful lights. And here that's form in the atmosphere, okay? So again, one of the things that is actually an important structure is the ozone layer, which is an important structure, and ozone is basically oxygen 3. So you have 3 atoms of oxygen that they share their electrons in a bond, and that is what the ozone is, okay? Now, ozone plays a major role in basically the protection of the Earth because it could absorb, in addition to oxygen, the normal oxygen is O2 and the ozone is O3. So they could absorb ultraviolet radiation, which is UV, is really high energetic radiation from the sun that could destroy life. Basically, they are extremely high energy that they are used actually in the hospitals nowadays for contamination, to eliminate contaminated basically microbes and things like that. So they are used as disinfectant. So it's a very high energy that could kill a lot of the organisms on Earth. So what you do in this case is radiation comes in, breaks down the oxygen O3 or breaks down the oxygen O2, and then basically the radiation is absorbed, but it's emitted back in a less dangerous one, which is in the visible range or even longer wavelength. So in that case, it's harmless, okay, or at least less harm than the other one, because even infrared can cause heat. So but the point being in here, this is basically what happened. But when you send chlorine, for example, in the atmosphere, that destroys the ozone and combines with the oxygen, and basically you'll have less, the atmosphere will be exposed. So here is a picture again. So you have UV radiation. UV is infrared, ultraviolet, I'm sorry, ultraviolet. So here is a spectrum of the visible light. So you have the violet in here. You have the red in here. You have the infrared in here. And you have the UV here. There is actually more damaging than that is the X-rays. And there are more damaging than that are the actually gamma rays. Gamma rays are not produced hardly with the sun, but they are actually produced nonetheless. And then X-rays, they are actually absorbed by the atmosphere. But the UV, they penetrate the atmosphere, and the only place that stops them is the ozone layer. And they are dangerous. The ultraviolet are dangerous. Then you have the visible. The visible is what we see. That's actually how we can see things. Okay, that our eyes evolved to be in that range, because that's the radiation that goes through the Earth and comes to us. And then you have the infrared, which is heat. Okay, so this is basically what's going on in here. So you have the atmosphere in here that absorbs the high energies. Then the UV comes in, and it's also absorbed in the ozone. And then light goes through. When light goes through the Earth warms up, of course. I mean, you and I, when we absorb light, anything absorbs light, is going to basically get excited just like the others, whether the atoms or the molecules get excited. So they are emitted back. And when we are emitted back, because our temperature is not that high, we most of the time emitted in the infrared, in this region. That's why when you use goggles to look at people at night, that you see with the goggles there, they use actually the microwave and the infrared wavelengths to detect objects, because they are cooler than any other object. Then, for example, the higher temperature objects that emit in the red, for example, if you take a spoon and you warm it, it's going to be red. Okay, at some point it's going to be dark, and then it's going to start changing color. So the point being in here is now you are emitting in the infrared. Well, the atmosphere itself will reflect the infrared, especially if it has a lot of carbon dioxide or water in its surface. They actually trap the the infrared. So now this infrared goes back to the Earth and never leaves actually the Earth. So it's in the sense they're actually they're trapping the infrared, causing, and infrared is heat, so causing the surface of the Earth to heat up, because now the Earth is still receiving the other wavelength. So it's still getting more energy in it, but this energy is not escaping, it's staying in the atmosphere, okay? So that is really part of the problem in here. So the heat is being absorbed and retained. So this is what we mean by the greenhouse effect. The greenhouse effect is real, and it's tied to the human activity, okay? The studies actually confirm that. And this is something that is actually a warning that you have to be careful with it, because it might lead to a non-return point. Basically, at some point, we're going to reach a point where we cannot recover from it. So this is what science is saying. And if we release more carbon dioxide in the atmosphere, then that is only the consequence of that. If we destroy more the ozone, that is going to cause UV radiation to go through, and that is actually damaging to life. So this is the atmosphere, and the global warming, as I was saying in here, is real, and the surface temperature of the Earth has been increasing, and that could lead to consequences, devastating consequences. I want you guys to focus on the units that are coming, especially unit 41. That is from next week, where we're going to talk about Venus and what happened to it. And this is probably what we think happened to it in the past, so that it has went through a runaway greenhouse effect that caused the planet to heat up because it's the hottest object in the solar system. Of course, I'm not talking about the sun, okay? The other thing also that is of interest to us are the Melakovich cycles. One of them is the fact that the axis of rotation of the Earth. Let me finish with this last 2 points in here. Basically, the Melakovich cycle is basically, remember, this is where the plane of the ecliptic is. This is where the Earth is going to be if it's spinning at 90 degrees, but it's not spinning at 90 degrees, it's spinning at 23.5 away from 90 degrees, okay? So that means that it's spinning around this cycle. At this point, that is pointing toward where Polaris is, but it was never pointing to Polaris all the time. It actually moves around. So in other words, the Earth is like a top, for example, like the toy that you guys play with when you were young. I have one, okay, somewhere inside. Basically, it's going to spin, but it's going to spin at an angle, and there is a precession. That precession takes about 26,000 years. That's one thing. That's one of the cycles. The other cycle also is the fact that the eccentricity of the Earth changes over time. It's not always at this low value. Right now, it's actually very close from a circular value, meaning the seasons are more regulated, meaning the maximum distance from the Earth, which is about 153, the Earth from the Sun, I'm sorry, which is 153 million kilometers, and the closest the Earth can get from the Sun, which is 147 million kilometers, give or take this 3 million kilometers, basically ventures 6 million kilometers one way or the other. This is a low number, meaning the path of the Earth is very close from a circle. But at some point, it's actually more accentuated, more elongated in a sense. There is more difference between the furthest away from the Sun, namely the aphelion, or the aphelion, and the closest point from the Sun, or the perihelion. So there is more difference between them, which leads to extreme seasons, okay? That in addition to the tilt of the Earth that is changing. So this impacts, of course, the weather on the surface of the Earth, and this impacts also the Earth overall, and its surface and its temperature and how much gases are released and so on and so forth. Well, the weather of the Earth is actually influenced far more on a daily basis than that of the Melakovich cycles, namely the Coriolis Force, okay? Coriolis Force is the one that is responsible for hurricanes and all kinds of weather phenomenon on the Earth, because if you go, for example, to the toilet and you flush it, you will notice that the water will cycle one way, whereas in the southern hemisphere, it should cycle in the opposite direction. That causes actually the upper atmosphere to be rotating in one way in the northern hemisphere versus the other one in southern hemisphere. You need to remember this when we come down to especially Jupiter. We're going to talk about basically the big red spot on its surface, but that feature is not unique just to Jupiter. There are actually more winds and faster winds on Saturn than that of Jupiter, and that motion, because of the way the planet is spinning also around its own axis. As a matter of fact, when we talk about Jupiter and Saturn, we'll see that they move faster than the Earth. In other words, if you were to stand on the surface of Jupiter, the day there is shorter than the day on the Earth. It lasts only about 10 hours on either one of them, whereas here the day is about 24 hours. So this is important because the spiraling, and that causes actually also hurricanes, except those hurricanes are on a gigantic scale. And like the ones that we have in here, they last for about a week or something. Ian, which is devastating, there's no question about it, but it's really a child play compared to what's going on on the surface, for example, of Jupiter or Saturn. One of the hurricanes, for example, on Jupiter has been noted going on for about 300 years now. So we're not talking about 2 weeks or 2 weeks or even a year or 3 years. This is 300 years now, 3 centuries that hurricane is going on, and it never basically stopped. So this is something to give you an idea of what's going on. So the Coriolis force is when you have an object that is moving, like for example, the case of the Earth that is spinning, and on top of that, you have an object that is going around it, circulating, in this case, the air masses and the atmosphere due to the weather, especially, which is really related to the pressure, which is related to the temperature gradient. One region is hotter than the other, so the air moves from one region to the other to fill the gap. But then the planet is moving, so that causes Coriolis force in this case, and that force is the one that is responsible for all of these things. Okay, I wanted to cover all of the stuff that is related to these units, but the biggest emphasis this week is going to be the midterm by far. Okay, we wanted to make sure to do the review before it's over on tomorrow at midnight, when the review is going to expire. You do it for two reasons, and I know I mentioned that before, and I mentioned in the messages that I sent them, but I'm repeating myself for a reason, because I know the weight of the midterm is the highest. So that's why you need to prepare and prepare for it well. So you need to do the review because it's a graded assignment and also helps you prepare for the exam. The other things also that you need to do this week are the assignments that are due this week. I know homework assignments, and I know also the discussions. But also we have a new stuff that is also happening this week, namely the project that is starting this weekend, namely starting this Sunday, and then it's going to last for 4 weeks from after that, where you do on a weekly basis activity and you document your activity so that when you come time for the reporting, you have all of the things done for you. Sounds good, guys? In good shape? Yes, no, maybe? Okay, very good. Thank you very much. Okay, here is the thing then. We don't have a live session this Wednesday. Okay, we have lab for those sitting in the lab, but we are meeting on Monday, and I know we have other assignments, and most likely I will go more detail about this project on Monday, and also about the homework assignments and things like that. And then we resume our stuff on Monday with a normal schedule. So I'm going to stop the recording, and I will see you guys live again on Monday, October 10th. Okay.